Hi, it's Mark Palmquist. I just wanted to do one more video on fluid dynamics. There are a lot of books on fluid dynamics. I actually took fluid dynamics in college, and I want to do an explanation that is easier for people to understand, that does not involve um, calculus and lots of math. So my explanation is going to be based on Newton's laws of physics and the laws of conservation of momentum and also the Coanda effect. Okay, so you just saw a video of a spoon in a sink flowing through a stream of water. So the first thing that you'll notice is as soon as the spoon makes contact with the water, the spoon moves this way. And so how is that possible and what causes that? Well, it actually has to do with the law of conservation of momentum. As the water makes contact with the spoon, the Coanda effect basically makes the water stick to the surface, and the direction of the water changes so that when the water leaves the tail edge of the spoon, it continues to go in this direction for a while. And because water cannot just change direction without a force being applied to it, there has to be a force in the opposite direction. So there has to be momentum, mass moving this way, and that's what the spoon does. So the water moves to the left and the spoon has to move to the right, and it has to do with conservation of momentum. And the direction that you can expect the spoon to move in is going to be, if you take this area of contact and you kind of bisect it, and you basically end up right here in the middle. That's where the spoon is going to move this direction. Okay, so here's a couple more examples of fluid flow. If you take the spoon and you orient it like this, I've exaggerated the shape to make it more like a semicircular shape. So the water hits here and then it's deflected in both directions, and then you can tell the drag by the total change and shift in direction of the water flow. So in this case, the water is still basically traveling in the same direction that it started out with. The water started out going in this direction, and now it's coming off the trailing edge and it's still going in that direction. So now the drag is not very high in this case, and the drag here is based on frontal area. So the wider this surface is, the more drag there will be, and the more narrow this surface becomes, the less drag there is. Okay, so here's the spoon rotated 180 degrees, and now the spoon is, the water is facing the spoon this way, and it's deflected, in this case, more than 90 degrees. So, so you're actually imparting more shift in momentum to the spoon. The water is imparting more to the spoon, and the movement will be in this direction. And so this has much more drag. So if you want more drag, you basically make a semicircular section, and that's why a parachute is basically a hollowed out semicircle. And it has to do with the change in the direction of the flow of the fluid coming off the edge. Okay, so let's look at an airfoil that's non-cambered. Well, it's supposed to be cambered, but it kind of looks asymmetrical. So imagine this is symmetrical. water flows here, and it splits. Half of it goes this way, half goes that way. And look at the trailing edge. It's basically going this direction. So if you draw an imaginary line this way and you split these two angles, this line is in line with the middle of this airfoil. So this airfoil will not have any drag on it. This will be the least amount of drag. And now the drag is determined by the frontal area and also some constant that has to do with the shape. And so people have experimented with shapes, and this shape tends to perform the best in terms of minimizing drag. Okay, so now here's a cambered foil. This is a typical lifting foil. This side is an arc and this side is an S. So if we draw a line here, the water flowing, or the fluid flowing off the tail edge does not go through the center of mass of this object. If you continue this line, it goes this way. So there's two things that have to happen to this. One, it has to move this way because it's going to kick the fluid this way. So the fluid is going to go like this, and it's going to go in this direction. So the fluid started out in this direction, and now it's... So the other thing is it has to rotate. So there's going to be a rotational force. This is going to want to rotate in this direction. So that's why airplanes have to have a tail, because if you don't have a tail, the cambered main wing will cause the nose of the airplane to dive. So this is... so like, let's look at a boat hull. Let's say this is a Hobie 16 and it's one side is flat and the other side is curved. And you have water flowing in this direction. So you can imagine, everybody talks about, oh yeah, this creates lift. So it pulls the boat towards the windward direction. The problem with this is the water leaving the back is in this direction. So the boat wants to turn away from the wind. Because this line, if you bisect this angle, it does not pass through the center of mass of this hull. So yes, you do have lift, but you also have rotation, and that's why Hobie 16 cannot point as high as a Tornado or some of the other boats that have a centerboard or a dagger board. Okay, so here's one more last example. Okay, so what if instead of a curved surface, you just have like a wedge? So fluid is hitting this wedge. And the reason I wanted to point this out is because this is very interesting. This is very similar to the cross section of my current hydroplaning wing, and so the water hits here, and then the pressure distribution curve kind of looks like this. So at this point, the pressure is the highest because it's immediately changing direction, and then it tapers down to nothing because by this time the center of lift would not be, it would be between here and here, but it would be about a third from the front. So, and it would be perpendicular to this wedge surface. So actually disregard this. The center of lift would be here. And what is the magnitude of this lift? Well, it's equally in proportion to the deflection of the water flow. But a thing that you will notice is the water, once it leaves this trailing edge, it continues to go down. You know, if this is up, then this is down. So it continues to go down for a while. So the total deflection of the water starts here and it ends here. It doesn't end at the trailing edge of the wing. It actually is some point beyond the edge of the wing. So that's why when you do all these mathematical computations of, you know, the lift that would be created on a hydroplaning surface, everybody's calculations are below what the actual lift is. So, and it has to do with this fact that the water is still being deflected, because it can't instantaneously change directions. So that is an explanation of fluid dynamics using conservation of momentum and Coanda effect.